Every year, 1.2 billion ounces of silver get consumed globally. Electronics, solar panels, medical devices, circuit boards in every smartphone, laptop and car. The industry tells you it's all recyclable. They publish reports showing recycling growth year after year. But here's what the numbers actually show. Only 158 to 180 million ounces get recycled annually. That's 15%. 85% of all silver used each year comes straight from mining, because the rest disappears forever into landfills, incinerators, and waste streams across the planet. The Romans recycled their silver denarii for centuries. We recycle less silver today than any civilization in history, despite having more of it embedded in more products than ever before. And here's what should terrify you. With every generation of electronics, solar panels and IoT devices, more silver enters the waste stream permanently, and the industry designed it that way because dissipative use is more profitable than recoverable use. Silver occupied a position in human civilization for over 3,000 years that bears almost no resemblance to its role today. From the minting of the first Greek drachma around 700 BC, through the collapse of the Bretton Woods system in 1971, silver functioned primarily as money. The Roman denarius contained approximately 4 grams of silver and circulated as the backbone of Mediterranean commerce for 5 centuries. When those coins wore down or were damaged, they were melted and reminted because the metal itself held the value. Spanish silver, extracted from the mines of Potosi in the 1500s, flooded Europe and became the foundation of global trade networks that connected 4 continents. American silver dollars, minted under the Coinage Act of 1792, established silver as legal tender in the United States, with each coin containing approximately 0.77 troy ounces of pure silver. Even as late as 1964, United States quarters and dimes contained 90% silver, and citizens could exchange paper silver certificates at any bank for actual metal on demand. The critical characteristic across all these centuries was simple. Silver in monetary form was designed to be recovered, recycled, and reused indefinitely. When a Roman denarius passed through 10,000 hands over 50 years, it could still be melted down and reformed into new currency. The metal never disappeared. The transformation began in earnest during the early 20th century, when industrial applications for silver exploded across multiple sectors simultaneously. Photography emerged as the first mass consumer technology that consumed silver in ways that made recovery economically impractical. Silver halide crystals embedded in photographic film and paper were chemically altered during the development process. And while some photographic silver could be recovered through specialized refining, the vast majority entered the waste stream permanently. Electronics manufacturing discovered that silver possessed the highest electrical and thermal conductivity of any metal, making it irreplaceable in switches, contacts, and circuit boards. Medical technology found that silver's antimicrobial properties made it essential for wound dressings, catheters, and surgical instruments. Solar panel manufacturing realized that silver paste printed onto photovoltaic cells provided the most efficient pathway for electron collection. Each of these applications shared a common characteristic that marked a fundamental departure from silver's historical use. The metal was being consumed in quantities so small, embedded in matrices so complex, and distributed so widely that recovery became physically impossible at scale. This phenomenon is called dissipative use, and it represents the crucial distinction between silver and gold that industry narratives deliberately obscure. Gold remains almost entirely recoverable because its primary applications involve forms that can be melted down and reformed. Gold jewelry, gold bars, gold coins, even gold used in electronics can be extracted and refined back to pure metal. The World Gold Council estimates that roughly 200,000 metric tons of gold have been mined throughout human history, and approximately two-thirds of that total still exists in identifiable, recoverable forms today. Silver followed the same pattern for millennia until the 20th century. Industrial Revolution changed the equation entirely. Modern electronics contain silver in quantities measured in milligrams, soldered onto circuit boards, alloyed with other metals, and sealed inside plastic housings that are designed for disposal rather than disassembly. Solar panels embed silver in microscopic traces across glass and silicon layers that cannot be economically separated. Medical devices use silver in forms that are contaminated, hazardous, or chemically altered beyond practical recovery. The metal does not disappear in a physical sense, but it becomes so dispersed, so mixed with other materials, and so expensive to extract that it might as well have vanished from the supply entirely. This is the foundation upon which the recycling illusion was built. The silver industry publishes annual reports that showcase recycling statistics with carefully chosen language designed to create the impression of a circular, sustainable supply chain. The Silver Institute routinely highlights year-over-year increases in recycled silver volumes, presenting figures that show millions of ounces recovered from scrap sources and industrial byproducts. These reports generate headlines in financial media suggesting that recycling is filling supply gaps and ensuring long-term market stability. The mathematical reality tells a fundamentally different story that industry narratives work systematically to obscure. Global silver consumption in recent years has hovered around 1.2 to 1.3 billion ounces annually, driven by electronics manufacturing, solar panel production, industrial applications, jewelry, and investment demand. Against this massive consumption figure, total recycled silver supply reaches approximately 158 million to 180 million ounces per year. The arithmetic is straightforward. Recycling contributes roughly 15 to 20% of total annual silver supply, which means that 80 to 85% of silver consumed each year must come directly from mining operations. This is not a temporary imbalance or a market inefficiency that will correct over time. It is the permanent structural reality of modern silver consumption. The rhetorical sleight of hand employed by industry publications involves presenting recycling growth rates without anchoring those figures to the baseline proportion of total supply. When a report announces that recycled silver increased by 8% year over year, the statement is technically accurate but functionally misleading. An 8% increase on a base of 170 million ounces adds roughly 13 million ounces to global supply. Meanwhile, total consumption increased by 50 million ounces during the same period, driven entirely by expanded electronics production and solar panel manufacturing. The recycling growth is real, but it is utterly dwarfed by consumption growth, meaning the gap between recoverable supply and total demand widens every year despite the positive recycling headlines. This creates a narrative environment where the public hears that recycling is growing and assumes the problem is being solved, while the underlying mathematics demonstrate that recycling is becoming less relevant to overall supply dynamics with each passing year. The comparison to other industrial metals exposes how deliberately misleading the silver recycling narrative has become. Copper recycling accounts for approximately 30 to 35% of global copper supply, nearly double the rate of silver, despite copper being used in far larger quantities and far more diverse applications. Aluminum recycling reaches 40% of supply in developed economies, with entire industries built around collecting and reprocessing scrap aluminum from beverage cans to automotive components. Gold recycling constitutes roughly 25 to 30% of annual gold supply, comparable to silver on the surface. But the comparison breaks down when examining the nature of the recycling. Gold recycled today can be re-refined to purity and used again in jewelry or electronics indefinitely. Gold that enters a recycling stream actually returns to the usable supply. Silver recycling figures include material that is technically recovered, but often in forms contaminated with other metals or mixed with industrial waste, reducing its utility and economic value. More critically, the 80 to 85% of silver that is not recycled does not simply remain in the ground waiting for future extraction. It has been consumed, dispersed, and rendered economically unrecoverable, representing a permanent contraction of the accessible silver supply that no future mining operation can replace. The numbers cannot be made up later because the physical material no longer exists in a form that can be captured, refined, and returned to productive use. Modern electronics manufacturing has engineered silver into products in ways that guarantee permanent loss of the metal from the recoverable supply chain. A typical smartphone contains approximately 1/3 of a gram of silver distributed across dozens of components, including circuit boards, switches, conductive adhesives, and electromagnetic shielding. That 1/3 of a gram represents silver worth approximately 10 cents at current market prices, embedded in a device that consumers discard after 2 to 3 years of use. The economic calculation that determines whether that silver gets recovered is brutally simple. Extracting 1/3 of a gram of silver from a complex electronic device requires specialized equipment, trained personnel, chemical processing, and energy inputs that cost far more than the 10 cents of silver the process would recover. The same calculation applies across virtually every consumer electronic device produced in the 21st century. Laptops contain roughly 1 gram of silver. Tablets contain half a gram. LED televisions contain 3 to 6 grams, depending on size. Automotive electronics contain 15 to 30 grams per vehicle. In every case, the silver exists in quantities measured in fractions of a gram, soldered onto circuit boards alongside dozens of other materials, including copper, tin, lead, plastics, glass fiber, and ceramic compounds. Separating silver from this matrix requires either acid leaching processes that dissolve the board and precipitate individual metals, or high-temperature smelting that burns away organic materials and melts metals into alloys that must be further refined. Both methods are energy-intensive, environmentally hazardous, and economically viable only when processing massive volumes of material or when targeting higher-value metals like gold. The global electronics waste stream generates approximately 53 million metric tons of discarded devices annually, making it the fastest growing waste category in the world. Of that total volume, only 17% enters formal recycling channels where precious metals extraction might occur. The remaining 83% follows one of 3 paths to permanent loss. Devices are landfilled directly, where silver remains locked in sealed components that will not biodegrade for thousands of years. Devices are incinerated in waste to energy facilities, where silver either vaporizes into ash or concentrates in slag that gets buried without further processing. Devices are processed in informal recycling operations, typically in developing nations, where workers manually disassemble electronics to extract copper wiring and aluminum heat sinks, while discarding circuit boards that contain silver into open burning pits. Each pathway ensures that the silver embedded in modern electronics never returns to the supply chain in any recoverable form. Even in the 17% of e-waste that reaches formal recycling facilities, silver recovery is not the primary objective. These operations focus on extracting copper, which makes up approximately 20% of electronic waste by weight and generates the bulk of revenue for recycling operations. Gold recovery is secondary, targeting the tiny amounts of gold used in high-value components like processor pins and memory contacts. Silver exists in quantities too small to justify dedicated recovery efforts, so it typically gets captured as a trace byproduct during copper and gold refining, if it gets captured at all. Solar panel manufacturing has created an even more insidious form of permanent silver loss. Photovoltaic cells require silver paste printed in microscopic traces across silicon wafers to collect electrons generated by sunlight exposure. Each solar panel contains approximately 20 grams of silver, which sounds substantial until examining the physical structure. That silver is printed in lines 100 micrometers wide, sintered onto silicon at high temperatures, and sealed beneath layers of tempered glass and polymer backing. The panels are designed for 30-year outdoor lifespans, during which the silver becomes chemically bonded to the silicon substrate. When panels reach end of life, they enter waste streams, where no economically viable process exists to separate 20 grams of silver from 40 pounds of glass, silicon, aluminum framing, and polymer layers. The solar industry has installed over 1 terawatt of photovoltaic capacity globally, consuming billions of ounces of silver that will never return to productive use. This is not an accident of engineering. This is the deliberate design of products optimized for manufacturing efficiency and cost reduction, with zero consideration for material recovery. The scrap supply narrative operates through statistical aggregation that deliberately obscures the fundamental shift in what gets recycled and why those changes matter for long-term silver availability. When industry reports announced that recycled silver reached 175 million ounces in a given year, that figure combines multiple sources with vastly different characteristics and recovery rates. Jewelry scrap contributes a significant portion, representing silver that exists in forms specifically designed for melting and refining. Sterling silver flatware, old coins, decorative items, and broken jewelry enter recycling channels through pawn shops, jewelry stores, and dedicated precious metals dealers who pay near spot price for the material. This category of scrap is economically viable to recycle because the silver exists in high concentrations, typically 92.5% pure in sterling silver, and requires minimal processing to return to usable form. Photographic scrap once represented another major source, with used X-ray films, photographic papers, and fixer solutions containing silver halides that could be chemically precipitated and refined. Industrial scrap from manufacturing processes contributes material like silver-bearing solutions from electroplating operations, off-specification products from electronics assembly, and production waste from solar panel manufacturing. Each of these sources shares the characteristic that made silver recycling viable for centuries. The material exists in concentrated, accessible forms, where the value of recovered silver exceeds the cost of recovery by a comfortable margin. The critical deception embedded in aggregate recycling statistics is that they present these disparate sources as if they were interchangeable and sustainable, when the reality is that the easy sources have already been strip-mined. Photographic silver recycling peaked in the late 1990s when film photography dominated the consumer and medical imaging markets. A typical chest X-ray film contained approximately 1 ounce of silver, and hospitals, dental offices, and medical imaging centers generated massive volumes of used film that entered dedicated recycling streams. The transition to digital photography and digital radiography eliminated this source almost entirely within 15 years. By 2010, photographic silver recovery had collapsed by more than 70% from peak levels, removing tens of millions of ounces annually from the recoverable supply base. Jewelry scrap follows boom and bust cycles tied to silver prices and economic conditions. When silver prices spike, consumers liquidate holdings and old jewelry floods the market. When prices stabilize or decline, jewelry scrap volumes contract because the financial incentive to sell diminishes. More fundamentally, the stock of recoverable jewellery has been depleted through decades of high silver prices that motivated liquidation. Sterling silver flatware sets that were wedding gifts in 1950 have already been sold. Victorian silver tea services have already been melted. The jewellery scrap that sustained recycling volumes for generations is largely gone, replaced by lower purity costume jewellery and fashion pieces that contain minimal silver content and offer negligible recovery value. Industrial scrap represents the remaining pillar of the recycling narrative, but this category disguises a crucial distinction between recyclable and recoverable material. Manufacturing waste from electronics production or silver refining operations can be captured and recycled because it exists in concentrated forms within controlled environments where collection systems are already in place. This is fundamentally different from consumer electronics that have been sold, used, discarded, and dispersed across landfills and waste streams globally. Industry reports count both categories as recycled silver, creating the false impression that consumer products contribute meaningfully to scrap supply, when in reality the overwhelming majority of recycled industrial silver comes from manufacturing byproducts that never left the factory. The growth rates that generate optimistic headlines about increasing recycling volumes are anchored to these ever-shrinking bases. When photographic scrap contributes 50 million ounces and drops to 10 million ounces over a decade, a 5% annual increase in jewellery and industrial scrap might technically produce growing total recycling volumes while the actual pool of accessible material continues to contract. The statistics become a shell game, where declining sources get replaced by marginal increases elsewhere, producing headline growth that masks structural depletion. The public hears that recycling is expanding and assumes the silver supply is secure, while the composition of that recycled material shifts inexorably towards sources that cannot scale and away from the consumer products that contain most of the silver being consumed today. Geological attrition describes a phenomenon where economically valuable minerals become functionally extinct, not because deposits have been exhausted, but because the material has been dispersed into forms and locations that render recovery impossible within any realistic economic framework. Silver, extracted from mines and consumed in modern applications, enters this state of geological attrition at unprecedented rates, creating a supply crisis that operates invisibly beneath the surface of official statistics and industry narratives. When silver gets mined from a deposit in Peru or Mexico, refined to purity, and then manufactured into electronic components that get soldered onto circuit boards, shipped to consumers, used for 2 years, and discarded into municipal waste streams, that silver has effectively returned to a geological state. It still exists as atoms of silver scattered through landfills or incinerated into slag, but it has become as inaccessible as if it remained buried in ore deposits thousands of feet underground. The difference is that silver in the ground can potentially be mined if prices rise sufficiently to justify extraction costs. Silver dispersed through global waste streams cannot be economically recovered at any price point because the infrastructure, technology, and energy required to collect, sort, and process the material at the necessary scale does not exist and will not exist within any foreseeable economic scenario. Studies of electronic waste flows reveal that precious metals locked in discarded devices represent a materials crisis of staggering proportions that receives virtually no public attention. Research tracking the fate of smartphones, laptops, and consumer electronics demonstrates that recovery rates for precious metals, including silver, rarely exceed 15%, even in developed nations with formal recycling infrastructure. The United States generates over 6 million tons of electronic waste annually, containing an estimated 300 million ounces of silver embedded in components scattered across that waste stream. Current collection and processing infrastructure recovers fewer than 45 million ounces, meaning that roughly 255 million ounces of silver enter permanent waste disposal every year from American e-waste alone. Extrapolating globally produces numbers that dwarf mining output. The 53 million metric tons of annual global e-waste contains an estimated 1.5 billion ounces of silver, and existing recycling operations recover perhaps 200 million ounces, leaving 1.3 billion ounces permanently lost to landfills, incinerators, and informal disposal. This loss is not theoretical or temporary. It is permanent and cumulative, growing larger with each generation of electronic devices that enter the consumption cycle. The collection infrastructure required to reverse these losses does not exist in most of the world and shows no signs of development at necessary scale. The European Union maintains the most comprehensive e-waste regulations globally through directives that mandate collection targets and producer responsibility. Yet, European collection rates still hover around 42% of electronics sold, meaning that 58% of devices escape formal recycling channels. The United States lacks federal e-waste legislation, relying instead on a patchwork of state laws that create compliance confusion and enable massive leakage of discarded electronics into standard municipal waste. China, India, and Southeast Asian nations that manufacture the majority of global electronics have nascent or non-existent formal e-waste collection systems, ensuring that hundreds of millions of devices get processed through informal sectors where precious metals recovery is entirely absent. The economic incentives that might drive infrastructure development do not exist because the value of silver in individual devices is dwarfed by collection and processing costs. A recycling operation would need to aggregate tens of thousands of smartphones to make silver recovery economically viable, but the logistics of collecting, transporting, and storing that volume of mixed electronic waste before processing creates cost structures that eliminate any profit margin. The result is a global system where silver enters products by the billions of ounces annually and exits into permanent waste streams at nearly the same rate, creating what can only be described as technological geological extinction. Unlike natural geological processes that concentrate minerals into economically viable deposits over millions of years, technological consumption disperses silver into forms that can never be reconcentrated, ensuring that each generation of devices permanently removes material from the accessible supply in ways that no future mining operation can replace. The silver market in 2025 operates under structural conditions that make supply deficits not merely possible, but mathematically inevitable, yet industry narratives and financial media continue to present recycling as a solution that will materialize when needed. The data tells a different story. Global silver demand ranges between 1.2 and 1.3 billion ounces annually, driven by expanding electronics manufacturing, accelerating solar panel installations, growing medical device production, and persistent investment demand from buyers who recognize silver's unique position as both an industrial commodity and a monetary metal. Against this demand stands total annual silver supply of approximately 1 billion ounces, composed of roughly 820 million ounces from mining and 170 million ounces from recycled scrap. The arithmetic produces a structural deficit of 200 to 300 million ounces per year that gets filled by drawing down above-ground inventories that have been accumulating for decades. Those inventories are finite and shrinking, creating a supply crisis that has no resolution within current production and consumption patterns. Contemporary technological drivers ensure that silver consumption will accelerate rather than stabilize, locking ever larger quantities of metal into permanently unrecoverable applications. The global transition to renewable energy mandates solar panel installations that currently consume approximately 120 million ounces of silver annually, a figure projected to reach 250 million ounces by 2030 as nations pursue carbon reduction targets. Electric vehicle production embeds silver in battery management systems, charging infrastructure, and advanced electronic controls, with each vehicle containing approximately 1 ounce compared to 0.2 ounces in conventional automobiles. The expansion of fifth-generation wireless networks requires silver in antenna arrays, signal processing equipment, and network infrastructure deployed across millions of cell towers and base stations globally. Artificial intelligence infrastructure represents an emerging demand source as data centers multiply to support machine learning operations, with each facility consuming silver in server components, cooling systems, and power distribution networks. Internet of Things devices, projected to reach 75 billion connected units by 2030, will embed silver in sensors, circuit boards, and communications modules distributed across homes, factories, cities, and transportation networks. Every one of these applications shares the characteristic that defines modern silver consumption. The metal gets embedded in complex devices in minute quantities that make recovery economically impossible, ensuring that the silver consumed today will never return to the supply chain, regardless of future prices or technological advances. Mining operations cannot expand production to fill this widening gap because of fundamental structural constraints that rarely appear in discussions about silver supply. Approximately 70% of mined silver comes as a byproduct of copper, lead, and zinc mining operations, where silver is a secondary revenue source rather than the primary target. These base metals mines operate on economic models driven by copper or zinc prices, meaning that silver production from these sources responds to base metal economics rather than silver demand. When copper prices fall, mines reduce output or close entirely, taking their silver production offline regardless of silver market conditions. Primary silver mines that target silver as the main product account for only 30% of global supply, and investment in new primary silver projects has collapsed over the past 2 decades as major mining companies shifted capital toward copper, gold, and battery metals. The result is a global mining industry structurally incapable of responding to silver demand growth, locked into production levels determined by base metals economics, while industrial silver consumption accelerates, driven by technologies that guarantee permanent material loss. The recycling narrative provides cover for this reality, allowing industry participants and financial analysts to project supply adequacy based on theoretical recycling potential that will never materialize at scale. The invisible supply contraction proceeds unchallenged because the losses occur gradually across millions of individual products discarded into waste streams worldwide, creating a crisis that remains hidden until inventories are exhausted and physical shortages become undeniable.